I'd like to introduce the idea of ray diagrams. So ray diagrams describe the path that light takes. Light is actually a wave. It's a wave that spreads out in space. It's not a nice, neat arrow going along. It's much more complicated than that. But making ray diagrams is a nice way to simplify what's going on to help us to understand it. Ray diagram for a plane mirror. What this is saying is if there's a person standing here. So if I look at the light that's coming from this person's feet, so it goes out in all directions, but the particular bit of light that comes out of this foot and ends up in the camera bounces off the mirror here. So there's a mirror here, incident light from the foot hits here, gets reflected off and back into the camera. From the top of the head, the light there that goes to the camera goes at a different angle, but it still hits with an incident and a reflected ray. To the camera, this looks exactly the same as this. If the person wasn't actually standing here, if the person was over here, the light comes up here, hits the camera like that, the light from the head comes through and hits right here. So if there were no mirror and no person standing here, what the camera sees is exactly identical to having the mirror and the person. And notice, okay, this HO, that's an O, not a 0. That's the height of the object. DO, that's the distance from the object to the mirror. Then this over here, if what's really happening is a person standing here and being reflected, this is called an image. So to the camera, it appears exactly as though there was someone standing here. So there's an image of the person here. So this is height of the image and distance from the image to the mirror. That's what a ray diagram looks like for a plane mirror. Plane means a flat surface. So this is a flat mirror. So seeing a picture of it just on the slides is not as good as actually seeing something in real life. I wish you were here to play with the lasers yourself, but as it turns out, I get to have all the fun. So I have here, this is a laser ray box. So it can shoot a laser beam. This laser is running parallel to the board, and I've put pieces of paper to make it easier to see the laser beam because you can't see it reflected off of the whiteboard very well. So you can see there's a laser beam going across there. And here I have a plane mirror. So if I take a plane mirror and I put it in the path of the laser beam so that the laser hits it exactly normal, that's at 0 degrees. Don't forget, all the angles measured off of a mirror are measured from their normal direction. So if the mirror is like that, then that direction, that's theta equals 0, okay? So theta equals 0 is there. This would be theta equals 90. So 45, something like that. So in this case, the incident beam is 0 degrees. The reflected beam is also 0 degrees. I can take the laser and move it so that it doesn't hit at a normal angle. And you can see the incident angle and the reflected angle stay the same. If I were to draw a normal vector on the mirror, normal vector would be about here. So the angle here below my hand and above my hand are the same. Those are the incident and reflected beams. Now, it doesn't matter whether I move the source or whether I move the mirror. So if I go to that direction, you can see that the normal direction is now moved up here. So if I bounce it at 90 degrees, then the incident angle is 45 and the reflected is 45. Something that people don't often realize, so I want to make sure to point this out, is that ray diagrams, the rays can go either direction. So I have another laser ray box here, and I just want to show you that if I take this one and shine it, so this is the incident and reflected, if I reverse it so that I'm shining this one straight up the reflected beam, it does exactly the same. So the ray is completely reversible.